All right, so good morning. Welcome to class. It is Tuesday, May 5th. So we're getting really close to the AP test. Your AP test is going to be next Thursday at 3 p.m. So a few things to kind of go through before we do that. The first thing I want to talk about are grades. So some people have kind of started slacking a little bit with grades, but the more I've kind of looked at it, I kind of realized that even though your GPA won't be affected by grades, it still sounds like the grade is going to appear on your transcript. So a thing to really think about is you send your transcript to colleges, they might not they're not going to see this grade affected in your GPA, but I could easily see them looking through your grades and saying, oh, how did you do during your online learning? Because that would be a really good way to test how do you work whenever you're not forced to work? Like, what's your actual normal work level? Are you going to be the person that just drops down to the minimum required to look good, or are you going to be the person who actually takes it on yourself to actually work and has self initiative, things like that? So even though it looks like your grade is going to be more on kind of like you either pass or you fail, and it's not going to affect your GPA, I could easily imagine colleges are going to really look at these grades. So I don't think these grades are going to disappear. So please don't just be content to get a 70. That might come back to bite you later. You might as well work and get your things in and try to get your grades up. All right, so there's that. The other thing, College Board has been putting out information. So if you go to your classwork tab, I've had this one up for a little while. Your very top thing is talking about how the AP test will work, and it links to that, and you have this nice short video that I would watch that goes through the different submission processes and what they want. One thing to look at is they want your AP ID at the tops of different pages. They want your initials right below that, and they want you to number your pages. So I was just talking with other people in the chat where they were wondering if you had to do this if you type your response, which is kind of what it sounds like they're trying to get you to do, is they want you to type your response. I would suggest if you do type your response and I would still put this in the header and your number up here. I would make your Word document before you go into the test. That way it's set up to automatically give you your page number. And then you can already make your header with your AP ID and your initials there. And that way you're not trying to format your Word document during the AP test. So that's one thing. The other thing, another big thing before I forget, mock exam. We're going to talk about your mock exam next class. And I'm going to go and I'm going to put the key up. So you're going to do corrections and you'll turn that in here. That means if you haven't done your mock test, you need to finish that by tomorrow afternoon. So I can put the key up there. If you haven't done it by then, what I'm going to do is I'm going to post a different mock exam, and you're just not going to earn a curve on it. You're going to get the exact grade you get, and that's going to go in the grade book. So this is your last opportunity to take the mock exam and get the curve. Otherwise, yeah, no curve. So we are going to talk about that last class. So you need to finish that mock test and get it in. Otherwise, you're just going to be stuck with a lower grade. And I'm not going to go easy on the makeup mock test because I'm having to do extra work in order to make that. And I'm usually a little bit bitter when I have to actually do extra work because people are lazy. So you don't want to take the makeup test. Let's just put it that way. All right. So we're going to look at this. So we have a normal assignment that we're going to be doing like we've been doing for the last few times. I gave you 2 previous AP test questions. These are actually the last 2 relevant AP test questions we're going to go over. Monday, we'll go over the 2 example questions that College Board has put out that are specific to this year's AP test. So we'll look at that Monday. And then we have a few things. Tuesday during tutorials, I would be here. When was the mock test assigned? The mock test was assigned a while ago. It's under online class. Or no, was it here? AP review. Where was it? After this. There we go. It was on April 15th was the mock test. So if you've already submitted something for the mock test, you don't need to submit anything for the new assignment yet. But yeah, so finish your mock test, submit it here April 15th, and you'll have to go through it's under the AP review. You'll have to keep hitting the show more twice until you find it, because there's quite a bit under the AP review. All right, so yeah, we're going to go through that. Tuesday during tutorials, I would suggest being here if you possibly can at 2. We're going to start going through and creating a cheat sheet with you. So we're going to look through the different topics and review just kind of a bit. I'm going to help you break that down, and we're going to go through different topics. I'm not going to tell you exactly what to write, but I'll kind of help you, and I'll be taking questions and help you kind of connect things. And then we will have class next Wednesday and Thursday morning. I know your test is Thursday afternoon. I know some of you have AP chemistry, and if you have other classes, don't worry about it. But the day of the test, we're going to do something. It's not going to be a real rigorous AP style question, but we'll have an activity that's kind of more loose review that kind of helps you think through things. So pay attention to that. We will be doing a class next Monday, Wednesday, and Thursday, and I really suggest you go to the tutorials next Tuesday, just because this is the very end, right up to the AP test. Just 2 questions, 50 minutes, a real nice good chance to do well and get a high grade on the AP test this year. All right, so those are things that are coming up to take a look at. The other thing is we have our sample submission for the College Board. So a few things under this assignment to really look at. So we have this checklist that they want. Will homework be assigned next week? I will assign 2 assignments next week, yes. One of them is going to be the practice exam that we'll do pretty much like we've done the other ones. The other assignment is going to be turning in the cheat sheet that you make for the test. So it's not going to be really hard homework. They're both going to be assigned on Monday. But yeah, talk to me if for some reason you have a lot of AP exams early next week, and then I can work with you on that if you're really stressed about getting ready for the other classes. This is probably going to be one of your first AP tests, though, looking at the schedule. So yeah, if you have other AP tests and you're stressing about the work, just tell me, and yeah, I can help you. All right, so these are things that you really need to look up. You really need to know your 8-character AP ID. This is on the College Board website. You can go there, click on your name, and then it should go. There's something like college, like your AP information that you can go and click on, and you can see your AP ID. If you can't find that, tell me and I can help you find it. But yeah, you can find it on your My AP. Follow the link. You're going to need to write your name. So exam date, things to know. Your exam date is going to be May 14th. And it's going to be at 3 p.m. The start time is 3 p.m. And they want you there before. They said something like 30 minutes before. They want you there at 2:30 p.m. So you'll have your link. Get there early and go through all that. Read through this. Make sure you have everything on here. Make sure you're kind of prepared for everything. It goes through things to expect. And then the other thing is you have this, where is it? Yeah. So we have this link that goes to the practice day experience, the exam demo. I want you to go through here. Every practice question we have from now on, I want you to go here. You're going to enter your AP ID, and it'll take you to a practice test where you have to fill out your information in 5 minutes, and then it'll give you a little sample question. It's not actually a question. It's pretty much just saying, go through, do this, turn this in, and submit something. So I want you to take a screenshot of all of these going through, getting to the login page. I want you to take a screenshot whenever you are able to turn in your assignment. And I want you to take a screenshot after you turn in the second part. So everything I want you to do, you're going to have to submit a screenshot, actually submitting the answer to it to this exam day experience. I can't obviously go in and look at your submission, but I want you to take screenshots or pictures that you're able to submit it. again, this is just kind of practicing how you're going to submit your AP test. So a few suggestions of things you can do. If you're writing on a computer, I would suggest typing into a Word document. You'll type your answer into a Word document. The questions are going to be set up to where it's can pretty much all be answered by typing. So it shouldn't be a whole lot of typing out different things in math. It should be a lot of words. So computer, I would suggest using a Word document. If you're doing this on your phone, then you can write on paper and take nice, clear pictures of the page to upload there. Either of those work. The only thing I don't suggest is trying to use multiple devices. You can only have the test open on one computer. So don't be trying to go take a picture from your phone, upload it onto your computer, then upload it from your computer to College Board. Don't be trying to use a whole lot of devices because you're setting yourself up with a lot of links that can fail throughout. So if you're using a phone, I would suggest writing on paper. If you're using a computer, I would suggest writing in a Word document of some form. But yeah, if you have any questions about that, just please keep asking them either in class today or during next class, or email me just other questions that you still have about that. All right, so I need you to turn in the 3 screenshots that you go through that. Which kind of calculator would I suggest? It's probably not going to be a whole lot of math. There's a good chance you don't even need a calculator. But obviously, it's just kind of whatever calculator that you have available. I would suggest that it definitely be some sort of scientific calculator, like some sort of TI, TI-83, TI-84, TI Nspire. Where's my other calculator? But even just a scientific calculator can be nice. So just some sort of scientific calculator should be good. Probably not going to need it. From the practice question they already put out, there was just absolutely no math that you had to do. It was just, here's an equation, explain why the equation works or doesn't work. Use this equation to justify a claim, use this equation to prove a claim wrong, things like that. So not a whole lot of math. It's the question that College Board put out for this year's AP test. Doesn't look like a lot of math. We'll go over that on Monday. But if you want a calculator to make yourself feel better, some sort of graphing calculator or just a normal scientific calculator should be fine. All right. So let's get into this. We've already spent quite a bit of time just talking. If you know other people, if you have other friends or just other people you normally work with, definitely suggest them that they watch this video because there's quite a bit of information here. College Board is just sending out information left and right. So that would be good to look at. All right, so finally, let's get into actually working through the question. So we have right here, we have a block A sitting on top of a table. We have a pulley right here. We have block B pulling on the pulley. This is a longer question, 25 minutes. It sounds like it's going to be 25 points for the 25-minute question is what they're doing this year, and 15 points for the 15-minute question. So here we have this problem explores how the relative masses of 2 different blocks affect the acceleration of the blocks. So block A of mass MA rests on a horizontal tabletop. So horizontal is important. Negligible friction between the block A and the tabletop. So no friction right here. Negligible means pretty much ignore, no friction. Block B of mass B hangs from a light string. Again, light pretty much just means no mass, so ignore the mass of the string, runs over a pulley and attaches to block A as shown above. The pulley has no mass, negligible, no mass, spins with no friction about its axle. So pretty much this pulley doesn't do anything. This pulley is just, all it does is turns the rope. It doesn't add any forces, doesn't need any torques to turn. It's just pretty much not there. We can ignore the pulley almost for this situation. And then the blocks are released from rest. All right, so everything starts at rest. So A, suppose that the mass of block A is much greater, not just greater, but much greater, so way bigger than the mass of block B. Estimate the magnitude of the acceleration of the blocks after the release. So A has a huge mass and B has a tiny mass. What's the acceleration going to be? Yeah, it's not quite going to be zero. It is frictionless, but it's going to be very close to zero. So the acceleration is going to be very close to zero, or acceleration is pretty much 0 meters per second squared. All right, and then let's kind of get in the practice of things that we're supposed to do. So put your ID 1, 2, 3, 4, 5, 6, 7, 8. My initials are AB. This is my page 1. All right, let's just kind of get in the practice of what they want us to put at the top of our exams. So the acceleration is very close to 0. It's not going to be exactly 0, but it's really close. And then explain without deriving or using equations. So, very close to 0. So, block A, it's a capital A, has large mass and is hard to accelerate. Right, pretty much just Newton's second law, force equals mass times acceleration, big mass, really hard to accelerate. Block B has a small mass slash weight and pulls block A with very little force. So block A has a really big mass, hard to accelerate. Block B has a small weight, right? Block B is being pulled down by gravity. So it pulls block A with a very little force, and that means we have a very small acceleration. All right, now B, we'll look at B before we look at the answer. Not B, 2, this is number 1. Number 2. Yeah, let's be really careful we actually use their formatting system, their numbering conventions they use. Now we're looking at the other extreme case, right? These are kind of the edge cases where we have one is really big and the other is really small. One has a big mass, the other is a small mass. Now block A is much less than the mass of block B. So A has a really small mass and B has a very big mass. And again, much less, much greater. So really big differences, not just small differences. Estimate the magnitude of acceleration of the blocks after the release. So B has a really big mass, A has a really small mass. What's the acceleration going to be very close to? What would the acceleration be if block A just didn't exist? So yeah, so it will be the mass B times acceleration due to gravity divided by mass A plus mass B. But we're pretty much saying that mass A is practically 0. So mass A is practically 0 compared to mass B. How does your equation reduce down? Because all of a sudden we would have, yeah, it would reduce down to pretty much just acceleration due to gravity. So your equation is 100% correct. That is the equation that would be happening here, mass A plus mass B. But we have here, mass A is extremely small, so we're just let's just call that 0. Mass B times acceleration due to gravity divided by mass B. We just get acceleration due to gravity. Yeah, so that is the kind of goal. It would be, this is kind of a limits question. It's what's the acceleration as mass A approaches 0? What's the acceleration as mass B approaches 0? So we can have those different cases. Mass B approaches 0, this whole equation goes to 0. Mass A goes to 0, this whole equation goes to G. But we don't need to use all that math. This whole part A is trying to get us to solve this without math. So we could just imagine block A has a tiny mass. So block A is pretty much not holding up block B at all. It's almost like block B is just being dropped. So we're just going to see that acceleration is very close to G, acceleration due to gravity, or 9.8 meters per second squared. All right, so we have to explain this. So we have block A has a very small mass and very little acceleration, very little resistance to acceleration. One way you can look at mass is mass resist acceleration. Big mass, big resistance to acceleration. Small mass, small resistance to acceleration. So A is a very small mass, so it doesn't resist acceleration very much. Block B has a large mass and weight. And that means that, therefore, block, how should I write this? So block B pulls block A with a large force. And putting these all together, therefore, we have an acceleration is very large and close to the maximum possible acceleration, the max possible acceleration of G. Right? Acceleration due to gravity is the biggest acceleration we can ever get out of dropping something, right? Acceleration due to gravity is if I just drop something without anything holding it back. Block A gets really close to just not holding this back at all, so we get really close to acceleration due to gravity. So all of our accelerations just by dropping something have to be between 0 and G. So these are just our cases where we get really close to 0 and G. So let's look at this. So part 1, examples of correct answers. So 0 acceleration, or small acceleration, or negligible acceleration, or much less than G, or much, much less, like those 2 less than arrows, much, much less than G. All right, so a correct answer, an attempt at a consistent justification. So we had a correct answer, and you tried to justify it. And your justification was consistent. So you said 0, and you attempt to justify it 0. I would say this is kind of an easy point to get. As long as you got a correct answer, and you wrote something that you tried to justify it, I would give you that point. And then the other point is actually a good, correct reasoning. So something talking about, here we have nearly 0. Block A is much heavier than, yeah, I guess I wrote way more than I had to, but that's just kind of me. So we have a very small acceleration. Block A has a large inertia, or large mass, so it won't speed up much, close to 0, because block B is so light that it can hardly budge block A, something like that. Or, yeah, just pretty much any of these. And then 2 correct answers. G, or 9.8 meters per second, 10 meters per second squared, or just about 9.8 or 10. It's not going to be exactly this because it still has some mass, which I would say it's close to that, not exactly that. And they actually let you have that even if you didn't put units, which is weird. So correct answer and correct justification. So here you could only get 1 point. You had to get the answer and justify it correctly. So it's not good enough just to get the answer without a good justification. So nearly to G, block B is almost in free fall, or block A barely resists. Yeah, because block A is negligible mass and the tension of the string is nearly 0. You didn't have to go to the internal force of the tension or anything like that. Yeah, mass of block A, much less than the mass of block B. Negligible friction between block A and the tabletop. I guess that would have been good to talk about negligible friction. Pulley has negligible mass and spins with, yeah, you can go through all of those. Questions on this one? I think those were more relatively straightforward. All right, so again, this year's AP tests, they obviously can't ask you to draw a free body diagram, but I could see them easily ask you to explain why the free body diagram is correct or incorrect. So we're kind of doing this backwards of how this year's AP test will work. So now suppose neither block's mass is much greater than the other, but that they are not always equal. So they're similar in mass, but not necessarily identical in mass. The dots below represent block A and block B, indicated by the labels. On each dot, draw and label the forces, not components of forces, which all these are going to be at right angles, so you shouldn't need to be drawing components of forces anyways. Exerted on the block after the release, represent each force by a distinct arrow starting on and pointing away from the dot. All right, so what forces act on block A, the one on the table? Normal force holding this up. Weight pulling this down. These are balanced. We're on a flat surface. The other forces? Tension. So tension is pulling this to the right. Is there friction? No friction. All right, block B. We have tension holding this up. Is this the same or a different tension than the one right here? It is going to be the same. And then let's put 2 lines because these tensions are the same, but not the same as those. It's going to be the same tension because the pulley has no mass. So pretty much everything they said about the pulley having no mass or friction means that these will be the same. If the pulley had a mass and or friction, these tensions will not be the same. We'll actually see this later on in this question. And then the weight of mass B, I should probably call this weight of mass A. Weight of mass B, bigger or smaller than the tension? Yeah, this weight has to be bigger than the tension. The weight has to be bigger than the tension because there's no friction here. Because there's no friction here, this block has to accelerate to the right. If this block A has to accelerate to the right, the string goes over. Block B has to accelerate down if the string is not stretching or compressing or things like that. So A has to accelerate right, B has to accelerate down, so the weight of B has to be bigger than the tension. And again, this year's test, more so it's going to be about you explaining that as opposed to actually drawing it, but we'll go through and look at it. So correct normal force on A, acceptable label capital N or F sub N, or writing out the word normal force. Or force on the table, yeah, anything else. So pretty much you got a normal force. Gravitational forces with accept labels. I would go a little bit more than just saying FG. I would say you should write FGA or force of gravity A or weight A. Or again, you can do mg. You can't write G, right? You can't just write these because these are numbers. G is at 6.67 times 10 to the negative 11 constant. Lowercase g is a 9.8 times 10 to the meters per second squared. 9.8 meters per second squared on the surface of the Earth. And we don't have any extra random forces on here. But yeah, I would write it either mass A times G or FGA. And then you have tension forces, string force, whatever, or some label indicating the force comes from the string or from, yeah, not acceptable. Yeah, and we can't use the weight here because this weight is not equal to the tension. So you can't say weight of B is equal to this, is equal to this. That would not work. All right, so again, more so this year's test is going to be you justifying free body diagrams as opposed to drawing free body diagrams. So I care more about the thought that goes behind these. So if you have any questions about the why I drew anything this way, ask those, because those are the more important questions for this year's test. All right, so derive an equation for the acceleration of the blocks after release in terms of mass A and mass B and physical constants as appropriate. If you need to draw anything other than what you have shown in part B to assist in your solution, use the space below. Do not add anything to the figure in part B. So this is an important thing. Don't modify previous parts of a question to solve for the next part of a question. If you need to solve for it in another part, rewrite it. Or you could say, as seen in this part, I get this. You can reference previous parts, but don't modify a previous part of the question. Another thing is don't draw a circle to a previous part of the question. Don't draw a circle and then draw an arrow. If you draw a circle and then an arrow, you're pretty much saying move this from here to here, and they no longer grade it on the previous part. So just a few things to think about. All right, so derive an equation for acceleration. Tam already got it. I think Daniel already got it. But yeah, going through. For acceleration, we're going to be using Newton's second law, net force, and I'm going to be looking at the total mass total, and the acceleration of the system. Right? Instead of looking at the individual masses, I like to look at everything all together. So which of these forces cancel out, balance out, and don't contribute to our net force? Tension. So these tensions are internal forces. It's like me sitting inside of my car and pushing. The car pushes back with an equal force, and that doesn't make the car go. And then also the weight of A and the normal force of A. So the only thing that's left over that actually contributes to the net force on the system is the weight of B. Now it says don't write anything here, but I could also write MBG. Don't write anything that will make the previous part incorrect. This is still correct, so I could write that there. So that net force is only caused by the weight of B. So I have mass of B times acceleration due to gravity is equal to the total mass. That's going to be mass A plus mass B times acceleration, and then I just divide those two masses over. So mass B times acceleration due to gravity divided by mass A plus mass B is all equal to acceleration. So yeah, like Daniel did, you can derive this first and then go back and use that to answer these questions. You just can't use that in your reasoning because I don't want you to derive the question. From the practice question they put out already, they put out one, they'll put out the second one later. You're not going to be deriving math like this. It would be more so they would give you this equation and they would say justify why this equation is correct for this situation. And so it would be more like you see this and you would have to say, oh, this equation works because I have acceleration is net force divided by mass. And then so we would see this is total. And so this equation works because the net force is only caused by the weight of mass B hanging over the edge. All the other forces are internal or balanced out by another force. And looking at our total system, we're dividing by the total mass because we're looking at the acceleration of the system as a whole. So more so you're going to be giving the equation and then going back and justifying the equation or saying why the equation doesn't work. All right, now for part D, consider the scenario from part A2 where the mass of block A is much less than the mass of block B. Does your equation for acceleration of the blocks from part C agree with your reasoning in part A2? So hopefully it should if you were right. Briefly explain your reasoning by addressing why, according to your equation, the acceleration becomes or approaches a certain value when mass A is much less than mass B. So I'm going to look at this kind of from a limit perspective. Again, let's try to answer the question before you even try to say yes or no. again, this should obviously be a yes, because they're saying you're trying to answer both correctly, and if you answer both correctly and then they don't agree, then you did something wrong. So they better agree. So let's look at the limit. So limit as the, this is part B, so mass A is much less than B. So limit as mass A goes to 0. So we're looking at that limit. So we would have mass B times acceleration due to gravity divided by mass A goes to 0 plus of your acceleration plus mass B. So we get mass B times acceleration divided by times gravity divided by mass B is just G. So we see according to our equation, so as mass A gets very small, therefore the acceleration goes to G. So it really is a limit question. You're either saying as mass A goes to 0 or as mass B goes to 0. So I know you all love limits and you can't get enough of them. All right, let's see what the points they gave. Hope I wasn't being too lazy here. So using separate Newton's second law equation for each mass, we did the alternate. This is how I normally do it. I don't like creating two equations with a system of equations. You can do that. But for writing a whole system equation for total mass that does not contain internal forces, so not containing internal forces means we didn't include tension because that internal force balances out. We also didn't use the normal force or weight of A because those balanced out. So we have net force is the total mass times acceleration. So net force, the only force we have acting on the system is mass B times acceleration due to gravity. Mass A and mass B are total mass when we add those together times acceleration. And then we solve it from here. Now, we actually probably should look at that. We could get another set of equations. Now, this is not to be included in here, but they could easily give us these two equations here. So I could see an equation for mass A, these two forces balance out for A. So I could easily see tension is that net force is equal to mass A times acceleration. And then I could look at these two forces and I could see that the big minus small, so this would be for mass A, this would be for mass B. I could see that big minus small, mass B times acceleration due to gravity minus tension is equal to mass B times acceleration. And then I could go and I could substitute these two equations in order to get a final answer. So I could do tension is equal to this. So I could do mass B times acceleration due to gravity minus mass A times acceleration equals mass B times acceleration. And then I could add this to the other side, factor out acceleration, and then divide this over. I get the same equation. But this is a good thing to be able to see how to do. Get an equation from here. Net forces tension is equal to mass A times acceleration because I'm only looking at mass A. Big minus small, mass B times acceleration due to gravity minus tension equals mass B times acceleration. They could easily give you that equation instead of the system equation for this test. So make sure you can also look at those. All right. And then, yeah, we did that. Did I actually look through the other points? I think I scanned through it real fast. So yeah, we did that, and then writing the correct whole system. Yeah, you get that full point, and then a correct equation with supporting work. Oh yeah, here we are. So correct answer is yes, it should match. No is acceptable if the equations are inconsistent. So if you got A2 wrong and then you got an answer that was different, then you should write no. And then for a valid reasoning that addresses the result in part C and the reasoning in part A2. So valid reasoning, it has to be correct and you have to address both parts. So you have to be correct and address both of them. And then, yeah, this is the different ways you could do the points. So mass A much less than B, so it can be neglected in the equation. Yeah, they go through different ones here. All right. And then finally, part E, while the blocks are accelerating, the tension in the vertical position and the vertical portion of the string is T1. So E, what they're getting at is we have T1 here, and then we have a mass B times acceleration due to gravity is the weight of object B, is what they're saying. But now, next, the pulley of negligible mass is replaced by a second pulley whose mass is not negligible. When the blocks are accelerating in this scenario, the tension in the vertical portion of the string is T2. How do the two tensions compare to each other? Are the tensions going to be the same now that the pulley has a mass? No, they won't be. That tension 2, is that pulling more or less mass? Well, T1 pulls, yeah, it is going to be more. So T1, this is the tension with the massless pulley. This one pulls block A only, and then the pulley is negligible. So we can ignore the pulley for T1. But T2 pulls the block A and the pulley with a non-negligible mass, with a non-zero mass. So T1 only has to pull block A when the pulley has a negligible mass. T2 pulls block A and that pulley with a non-zero mass. So if you have to pull more mass, you're going to have a bigger tension. So we're going to see that T2 is going to be bigger than T1. And that's just the thing to not overthink too much. Just if I pull a little mass, it's going to be a small tension. If I pull a big mass, it's going to be a big tension, as long as I'm keeping the hanging mass the same. Let's do the reasoning here. So T2 is bigger than T1. You can still earn a point if you select the incorrect answer. So again, only select the answer if you're after you've worked it out and you're certain. If you get to the point and you're unsure if you're correct, just don't select an answer. You can sometimes get more points by not selecting an answer if you're unsure. So reasoning the acceleration, yeah, you could do that. I just like that explanation. Yeah, here we go. I like this one a little bit more. So the pulley can spin with negligible friction about the axle. The original pulley has negligible mass. The second pulley's mass is not negligible. The rotational inertia, yeah, smaller. I don't know why they want to keep going to accelerate. I mean, I get it. You can do accelerations for all this. I disagree with having to go through all of that. But yeah, you can relate it to accelerations. You have more, the pulley has a rotational inertia, and so that is harder to pull, so your acceleration goes down. If you have a smaller acceleration, then the difference in these two forces has to get smaller, so you end up having a bigger tension that's closer to the weight of block B. Yeah, I'm surprised they don't have an alternate answer for mine. Yeah, if you go through this technical answer from mine, I wouldn't get those points because I didn't talk specifically about acceleration. I would think mine qualifies for an alternate answer, but yeah, you could go through and actually relate these all to accelerations. All right, any questions on those? Does that make sense what I said, how they're trying to answer it? What's that? I went on a rant about friction and torque. Yeah, it's not about friction. So the pulley does not have friction, so it still has negligible friction. What it really is it now has a mass, and because it has a mass, it has a rotational inertia. And so one way of looking at it is it takes up some of the force to cause a torque to make the pulley turn. So I was kind of relating it to it takes force to turn the pulley and it takes force to pull this mass. So if it has to do those two forces, it has to have a bigger tension here. But yeah, if you were talking about friction, you're not going to get that point because there is no friction. Any other questions? All right, I'm going to go through the next one relatively fast. There's going to be parts I'm going to kind of skim over because we don't need to do the experimental design question in very much depth because that won't be on the test. Now, we get through here. Again, I'm going on to my second page. So let's just get in the habit of now I'm on the second page. I still have the same ID 1, 2, 3, 4, 5, 6, 7, 8. College Board really needs to think about the security of their IDs, giving me consecutive digits like that. Initials AB. And this is my second page. Again, you can easily do this on a Word document, set up your formatting before the test. Well, AB, these are my initials, Alex Beverly. So you would write TB, Tambui. I wasn't actually using generic initials. That's just what my initials end up being. Or Daniel Wen, you would write DN. APID, I guess you could. I think they do. That's how they had it on their example, right? APID is that. Yeah, you could write that. I want you to write it on your practice things. I want you to write it like it is going to be on the AP test. So yeah, I want you to write those on your practice assignments. And if you're going to be writing this on a computer, I want you to practice typing your response. If you have additional things like pictures, because there are more pictures on this than there are going to be on the AP test, you can upload a picture of those separately. But yeah. All right, here we have a projectile launcher. So we have a spring inside of a tube, and we have a sphere that's attached to it that gets launched out of this thing. Projectile launcher consists of a spring with an attached plate, as shown in Figure 1. When the spring is compressed, the plate can be held by a pin at any of the three positions, A, B, or C. So I can pull it back to A. It gets stuck here until I pull the pin, and then it launches the mass. For example, Figure 2 shows a still sphere placed against the plate, which is held in place at position C, so it's being held right here until I pull the pin away, then it will launch. The sphere is launched upon release from the pin. A student hypothesizes that the spring constant of the spring inside the launcher has the same value for different compression distances. So they think that spring constant K doesn't matter where I compress the spring to, it's going to be the same. So the student plans to test the hypothesis by launching the sphere using the launcher, and we want to state a basic physics principle or law the student can use in designing the experiment to test the hypothesis. So again, not going to have to design an experiment, but I could easily see them asking which physics law or concept or principle applies here. There's a few we could use. What are a few principles or physics laws we could use to figure out the spring constant here? Yeah, it's just 3A. So we can use So you're talking about spring potential energy. So that's an equation. We want a physics principle or law. So you're correct. We can use spring potential energy, but what's the law that we would use that's associated with that? So Hooke's law is one. So Hooke's law. We can use that spring force is equal to spring constant times the displacement from equilibrium. Again, we're talking about magnitudes. So spring potential energy, what's the principle I would use for that? Or conservation of energy. So I wouldn't say spring potential energy. I would say or conservation of energy. I could see how the spring potential energy gets converted to kinetic energy or into gravitational potential energy, something like that. So either of these work. And Hooke's law, you can also kind of use this along with Newton's second law. So we could use Hooke's law and Newton's second law together. So we could also use force equals mass times acceleration. We would have to use both of these together. All right. And then using that, determining expression for the spring constant in terms of quantities that can be obtained, measurements made with equipment usually found in a school physics laboratory. This is where things get really messy because we can do this a lot of different ways. So I'm just going to go through the different ways we could do this. So I could do Hooke's law. So spring force is going to be equal to spring constant times displacement from equilibrium. So we'd have to figure out a way to get that spring force. Yeah, spring scale, that would be difficult because those work by stretching, not by compressing, not by pushing this into the spring. Um, I would relate the spring force to mass times acceleration. So the spring force is equal to, I would set this up sideways, is equal to the net force is equal to mass times acceleration. I would set this up kind of where whenever I release this, it has that spring force pushing the mass this way, and I have the normal force, and I have the weight. So we could do something like this where we figure out the acceleration experimentally through the tube. That's going to be iffy because we're going to have to use acceleration at an instant in time. So that's going to be really hard to get. So this is going to be a really difficult way of going about it. Whenever we would set up the experiment, we would have to be very careful how we do this. But we could do something like that. And then our spring constant would equal to the mass times acceleration divided by the displacement of the spring. So this is going to be really hard to do. Conservation of energy is going to be very much easier. This is difficult. Not impossible, but difficult. This is going to be easier. And what type of energy is going to be easier to measure? Kinetic or gravitational potential energy? I mean, it really doesn't matter. Yeah, we'll do easier. Let's say launch it horizontally. So horizontal. So if I launch this horizontally, sideways, we're going to be turning spring potential energy into kinetic energy. So all of that spring potential energy is going to turn into kinetic energy when it leaves the tube. So 1/2 spring constant times that distance that's the spring is compressed is going to be equal to the kinetic energy 1/2 mass times the final speed squared. So multiply both sides by 2. I'm trying to get spring constant, so I divide the distance squared. So spring constant would be mass times the final speed squared divided by the distance the spring was compressed squared. This is going to be easier to get because I just have to know how far the spring was compressed from equilibrium. mass of the marble, and the final speed, which I can get with a photo gate. And then what I would say is probably the easiest would be putting this thing vertical. When I put this thing vertical, now that spring potential energy is being converted into gravitational potential energy. So 1/2 spring constant times the distance the spring is compressed is going to be equal to mass times acceleration due to gravity times the final height that this thing reaches. So we're trying to figure out the maximum height this thing will launch to, multiply by 2, divide by the distance squared. So spring constant would be equal to mass times acceleration due to gravity times final height. Multiply both sides by 2 and divide by the distance the spring is compressed squared. Finding a position is normally easier than finding a speed, and finding a speed is normally easier than finding an acceleration. Right? Because think about it, position, I can just get that from a meter stick. Speed, I'm going to have to do some sort of change in position divided by time. Acceleration, I'm going to have to do a change in velocity over time, which means I'm going to have a change in position over time minus a change in position over time divided by a time interval. So it gets harder and harder to calculate. Position is the easiest to find because we can just directly observe it. Velocity is easier to derive than acceleration is because velocity, we need 2 positions over a time interval. Acceleration, I need 2 velocities over a time interval, which means I need at least 3 positions, actually. You can use 4. All right. I don't care so much about B. It's not going to be on the test, so I'm not going to go into it very much. It's just pretty much design a procedure that could be used to find the things. Final height, I could use a meter stick to get. Mass, I would use a scale. Position, I would use a ruler or a meter stick to figure out how far the spring is stretched or compressed. To get here, mass, I would use a scale. Distance, a meter stick or a ruler. The final speed I would get with a photo gate at the end of the tube is how I would do that. To get acceleration, I would need 2 photo gates. So again, you can still try to do B. I just don't care. Not relevant to this year's AP test. You can still do it. You can still grade yourself. But the concepts are a little bit more important. All right, so here, I didn't actually go through this yet, but an equation that is consistent with the relevant principle or law stated. So you can't just give an equation you can't say, I'm going to use conservation of momentum and then start talking about energy. So if you use conservation of momentum, you should have used conservation of momentum in the next part, or the, you can still try to still correct it, still go through, still read it. I'm just not going to spend time on it here. Just give yourself a quick grade and then just go through and correct it real fast. Um, but there are going to be some things in here I still want to talk about though. So we'll get through that and I'll talk about some of the other things. Valid equation contains measurable quantities, so the equations have to include spring constant, obviously, because we're trying to find the spring constant. And then for a correct and valid algebraic expression for spring constant, and it must be solved for spring constant. This is actually one of the few times that they say you actually have to solve it for spring constant. It can't just be unsolved. Let's see. B is talking about the procedure, test the hypothesis, and all of this. So there's a few things we can go through, like get the mass of the spring with the triple beam balance, the compressed distance, which we're going to have to get for all of these, ruler or meter stick. In reality, you're probably using a ruler for small distances. And launch speed of the sphere, some sort of either motion sensor or a photo gate works for that. Here, this is where we launch this thing vertically. This is where I was talking about the conservation of energy, triple beam balance, or electronic scale, anything like that. Compression distance, give with the ruler. Horizontal displacement of the sphere. Yeah, they're launching this thing as a... are they doing with this? This is weird. Oh, they're launching this as a horizontal projectile? That's just dumb. Does it say that it's launched horizontally and has to be launched horizontally? Launching the sphere. It doesn't say it has to be launched horizontally, but I think they're saying it needs to be launched horizontally. So, yeah, that's weird because I would just turn this thing vertically and launch it that way. Oh no. Here we are. Launch it vertically. This is dumb. I don't know why you would launch it horizontally and then go back through all of this horizontal launch and figure out how far it travels in the x direction. Then you can figure out the x speed, and once you know the x speed and direction, you can get the time. Once you have the time in the air, you can. I don't know why they're going through all that. This is excessive. This is silly. I don't know why you would launch it horizontally unless you're doing conservation of energy. I would launch this thing vertically. Triple beam balance, get how far we compress this with a ruler, and just figure out how high this thing launches with a meter stick. I would probably include a video recording device in there. Again, doesn't matter so much. All right, so don't care so much about that. Let's go on to C. Still grade yourself, still kind of correct it, but don't. Yeah, the spring scale, that's a really hard thing to use for this because spring scales are meant to hang things on them vertically, and so it's meant to measure things by stretching it, not by compressing it. Um, it's just a really hard thing to do. There there are things you could probably say an electronic force sensor. Um, these are things that actually exist. We don't have them, but they exist. Um, if you said something about a spring scale, I would want it to be. I'm sure there's spring scales that exist that are made to measure things by compression. It would have to be something like that. Um, yeah, it would just be hard to use a spring scale. They just normally function differently than what we need them to do here. All right, so C, describe how the experimental data could be analyzed to confirm or disconfirm the hypothesis that the spring constant of the spring inside the launcher has the same value for different compression distances. Now, this is something I could see more like on this year's AP test. How could I use the equation I got to confirm whether the hypothesis was true or not? Or they'll give me an equation and they'll say, does this equation prove this hypothesis? These are the types of things that I expect to see, not so much derive an equation and see if it proves it. How would I use any of these equations to prove the hypothesis? Well, let's look at the hypothesis. The hypothesis is that the spring constant of the spring inside the launcher has the same value for different compression distances. So how could I prove the hypothesis with any of these equations? Well, we're trying to see if the spring constant is the same for different compression distances. So what should we probably do? All right, so that's one thing. So we can graph something comparing compression distances. So probably looking at a graph here. So if I'm looking comparing spring constant to compression distance, well, I should probably be graphing something like, does that compression distance change the spring constant? Yeah, so I want to solve this for the spring constant like this. I want to do something where slope is going to be change in y over change in x. And I want my slope to be spring constant. So if my slope is spring constant, I need a constant slope, constant spring constant. So we could do something like from this one, we could graph mass times acceleration versus the amount that the spring is compressed. Or I could do from this equation here, spring constant, I want my y over my x, so mass times the launch speed squared divided by that compression distance of the spring squared, right? Because that's equal to my spring constant. Or I could go for my final graph, that 2 mass times acceleration of gravity times final height divided by the displacement from the spring squared. So again, I would see more like they're probably not going to make you make this graph. I could see them give you a graph and say, is this going to be a constant relationship? So we graph these. So graph any of these. And if the slope is constant or linear, we have a linear graph. So if we have a linear graph, the constant slope, then the spring constant is constant. So we would expect to see some sort of straight line. I could also see them ask what should be graphed where, just knowing in order to get a slope that's equal to something, solve for the thing that you want to be the slope, and then put everything in the numerator on the y-axis, everything in the denominator on the x-axis. And again, you're probably not going to be, I can see them ask what should you put on each axis in order to get a linear graph or something like that. I could easily see them asking that. Let's see what they were going for here. Comparing measurements of the spring constant or a suitable proxy to all three possible compression distances. Yeah, I really should say that. Graph all of these for position A, B, and C. So we really should say for all of them, be a little bit more specific there. And then for considering uncertainties and confirming the hypotheses, does it say to do that? Yeah, I mean, they don't explicitly say that, but yeah, I should also say that. So if the numbers are about the same. So for considering uncertainties and confirming the hypothesis, so something like this would be like there might be friction, or obviously it's experiments, so your data might be slightly off. So I should probably say something not if the slope is constant, but if the slope is close to constant, or if my best fit line is right along those. So if it looks like it's trying to be linear, I would argue 3 data points is not enough. But if the points line up to where they're about linear is what they're getting at. Yeah, if the numbers match with an experimental uncertainty, or if the slope is linear, if the best fit line is very close to being linear, something like that. All right, and then finally D. Another student uses the launcher to consecutively launch several spheres that have the same diameter but different masses, one after another. Each sphere is launched from position A, so they're all launched with the same amount of spring energy. Consider each sphere's launch speed, which is the speed of the sphere the instant it loses contact with the plate. Should really say it's launched horizontally. We'll assume it's launched horizontally. On the axes below, sketch a graph of launch speed as a function of sphere mass. Again, they're not going to ask you to sketch this, but from the sample question they put out, it seems like they would give you the graph here and then say, does this match your expectation? Why or why not? So you're not going to be drawing these graphs, but it's still important to be able to recognize, does the graph match what I expect to happen? All right, so I should probably start out with, we're launching different spheres with different masses, but they're all starting with the same amount of energy, right? So we're all turning spring potential energy into kinetic energy. 1/2 spring constant times that initial compressed distance squared, all from the same distance. The only thing that's changing is our final speed. So this is equal to 1/2 mass times that final speed squared, multiply both sides by 2. We're trying to figure out that launch speed versus the mass of the sphere. So let's try to solve for the launch speed. We'll divide mass over, so that final speed squared after the launch is going to be spring constant times the distance this thing is compressed squared divided by mass. Then I'm going to take a square root. Yeah, we'll take the square root. So we get the final speed is going to be the square root of spring constant times the initial distance is compressed squared divided by the mass. So when we're looking at this graph, we're trying to graph the launch speed, so that final speed versus the mass. So first of all, mass is in the numerator. So what is my graph going to look like? As mass goes up, is the final speed going to go up or down? As I try to launch bigger and bigger masses, it's going to be harder and harder to launch. So it's going to go down. Now, a few things here. One, I'm never going to have a zero mass object, so let's not start this on my y-axis, right? I'm never going to launch an object with zero mass. That just is kind of nonsensical. And if I have a frictionless surface, this is always going to launch with some speed. So I'm not going to get down to zero final speed. Even if I had some like million-kilogram object, if this has zero friction, that million-kilogram object will be moving at just some tiny, tiny rate. Now, 1 over, is that a linear relationship or some sort of curved relationship? So it is an inverse relationship, not linear, so we're going to see some sort of curve. So is the curve going to be concave down, or is the curve going to be concave up? So concave up or concave down? So is it going to pass through the axis like this, or is it going to be like asymptote? So like through the axis or asymptotes? That's the real big question. Does this thing go around like this and go negative launch speed, or is it going to go like this and is it going to approach a zero launch speed? Yeah, it's going to be an asymptote, right? So a way of looking at this is smaller and smaller mass, it's going to get much bigger launch speeds. It's going to asymptotically approach that. I'm not going to end up in a negative mass area over here. I'm also not going to be launching with negative speeds or even negative velocities. It's always going to launch forward. So it's never going to go to negative launch speed, something like this. So an inverse and an inverse square root graph look very similar. You can actually even kind of ignore the square root part for this. It's going to be like all of the inverse relationships are going to be some sort of curve. It's just how curved it is. Is it curved a whole lot or curved less? So it's just all talking about how gradual the curve is when we're talking about square roots or like inverse square root or inverse square, things like that. All right, so we see a few things. So here we get a point, curve where the launch speed always decreases with increasing mass. And I would argue if you have a straight line there, you're also good. It's just as you get a bigger and bigger mass, it's harder and harder to launch, so that speed goes down. And then the second point is the curve is entirely concave up. So at all points we're concave up, we can't curve down and then up like that. So if we have like two separate regions of the curve, you don't get that point. And the launch speed always decreases, so we don't reach that asymptote too quickly. And then we do see if this is just 1 over x relationship, the asymptotes will look the same. But because it's 1 over square root, we see this asymptote is a little bit higher. But notice they're not grading based off that. They're not saying, well, the y asymptote approaches the y-axis much more rapidly than the x-asymptote approaches the x-axis. So we don't care about any of those. We just care that you kind of realize, hey, as I get smaller and smaller mass, my launch speed goes up, but it doesn't make sense to reach a 0 mass. If I get to 0 mass, I have an infinite launch speed. So I'm asymptotically approaching infinite launch speed as I go to 0 mass. The other way of looking at it would be as my mass increases, as my mass goes to infinity, because I have no friction, my launch speed goes towards 0. I'm never going to end up with a negative over here. It's never going to randomly launch backwards just because I have more mass. So that's one way of looking at it, or just inverse relationship, inverse. I don't care if it's inverse square root, inverse cube. It's going to look something like this concave up curve, asymptotically approaching the y-axis and asymptotically approaching the x-axis. All right. This one went a little bit longer because I talked quite a bit at the beginning. Again, still look at B, still kind of glance through it, still grade yourself and do a correction. And your correction, you can that one you can just copy straight from the key. I don't care as much. But yeah, again, for this one, upload your response on the College Board website. Go through this, take the 3 screenshots where I can see that you uploaded each one, and then you're able to log in. If you're unable to get your AP ID, just email me, and I can get that to you on an individual one-on-one basis. Keep working on this, things that are coming up. Thursday, we're going to do the mock test corrections, so go through and do your mock test if you haven't done that yet. Otherwise, you're going to get a much more difficult mock test, and it won't be curved. And then next week, we will have class Monday. We'll go through the practice questions AP has released for this year's test. Tuesday after school, I'm going to start helping you make your cheat sheet. So Tuesday tutorials at 2, try to be there because I'm going to start helping you with that. Thursday, I'm going to be helping you even further go through your cheat sheet, go through a lot of different topics, and we're going to look at that. And then that was Wednesday, and then Thursday morning, I'll also be here and I'll be answering last minute questions, and we'll do some like a kind of nice, easy review activity that'll help you kind of figure out things. It's not going to be a really rigorous thing on Thursday. I don't want to like destroy your brain right before the AP test. So times of the classes next week. So we're going to have a class 10 a.m. on Monday. 2 a.m. on Tuesday, or 2 p.m. on Tuesday. It's not going to be a class. It's going to be, again, just tutorials, but I would suggest you show up to that because, you know, we're getting right towards the end of the AP test. So it's not going to be a real, like, I'm not going to work through problems exactly like I've done this time, but it's just going to be more going through the concepts and kind of loosely connecting the dots for you and answering questions. And then we'll have our normal class Wednesday at 10. And then I'll have another class Thursday at 10 because that's the day of the AP test. I'm not going to assign anything you have to turn in then, but it's just going to be nice, good review where I can answer questions, and we're going to try to put concepts together in a visual way. So hopefully that'll help you kind of have the concepts fresh in your mind without really going through and thinking too much in depth and tiring yourself out right before the test. So make sure you're there. I will post those all whenever they come out. I'll probably post them a little bit before. Otherwise, just keep working, keep your grades up, and have a good day.